Hello, Longhorns. Coming back for part two. There's always a video that's going to be a little bit longer than the rest of them, and this introduction was definitely one of those. So, in the effort to get it trimmed down a little bit, here's your part two. We were talking about your pendulum going back and forth. And I was trying to remind you that if they ever talk about a bob, what is the bob's trajectory? As they've labeled here, a bob is the ball found at the end of a string or the cord of your pendulum. So it's just what's rocking back and forth. They like to use examples such as a person on a tire swing, or they may talk about an acrobat because the motion is still the same. If you're also trying to think of something in your home that may have a bob, if you have an older grandfather clock, the little part that ticks back and forth, the small circle is exactly what we're talking about. Now, let's look at an equation and see what it looks like in equation form. We have a 0.42 kilogram block is attached to the end of a horizontal ideal spring and rests on a frictionless surface. The block is pulled so that the spring stretches by 2.1 centimeters relative to its unstrained length. When the block is released, it moves with an acceleration of 9 meters per second squared. What is the spring constant of the spring? For each of these problems, after you finish reading, I want you to kind of pause. These problems do get a little long, but what they're asking you, if you can visualize it, kind of makes sense. In this problem, we have a block, and they provide us with the mass of the block. And it's telling you that I have pulled this block or stretched the spring that it's attached to a certain distance. And we're trying to calculate how much is needed to have that restoring force, to put it back where it started. We're going to use the guess method for this one. So if you have your PowerPoint in front of you, go ahead and start labeling your given. Take your time and make sure you include your variables and your units of measurement. So, first things first, we have a 0.42 kilogram block. Anything measured in kilograms will be your mass. It's attached to the end of a horizontal ideal spring, which simply means you have a spring lying on its side that can be stretched left and right. It rests on a frictionless surface. So think about this board, the top of a table, or anything that's nice and smooth would be frictionless. The block is then going to be pulled and stretched, so our X is equal to 2.1 centimeters. When the block is released, it moves with an acceleration of 9 meters per second squared. And they've asked us to find the spring constant. So my unknown is going to be K. Our equation is still the same. F equals negative KX. Now, we've had several problems where our substitution step could actually be skipped. But in this example, let's pay close attention to our units of measurement. Your mass is in kilograms, so that's correct. Our displacement is in centimeters. We're going to go ahead and convert that to the standard unit of meters. So we're going to convert 2.1 centimeters to meters. For every 1 meter, I know that I have 100 centimeters. I have centimeters on the top and on the bottom, so that unit is going to cancel out. This will leave me with 2.1 divided by 100, which equals 0.021 meters. A common thing to do is to come back over to your given and cross this number out. Hopefully that will remind you that you have made changes and you'll plug in your new number instead. Our acceleration is already in meters per second squared, so we're ready now to solve this problem. Let's start with our original equation. But we notice that we were not given F in our given. But there's an equation for force. Force equals mass times acceleration. And we have mass and we also have acceleration. So we're going to expand our equation. M times A equals negative KX. My mass is 0.42. My acceleration is 9.0. My spring constant is my unknown, and we convert it. So we're going to input 0.021 meters. First, we're going to multiply on this side, so grab your device so that we can simplify a bit. 0.42 times 9 will give me 3.78. And I'm going to bring down my constant and my displacement. We now know that whatever number is next to our unknown, next to your variable, has to move. So we will now divide both sides by our 0.021. I have the same number on top and bottom. What's going to happen here? Those are going to cancel out. And we simply need to divide. Final answer should be 180. Now, what does the negative sign mean? Remember, we're dealing with those quantities that are vectors. So it's telling you that you're pulling that object back. So it's traveling opposite the direction that it was originally going in. All right? Now, let's check our units. We had kilograms, we converted to meters, and we also had acceleration. We were sure to do our substitution step. We ended up expanding our equation, and we ended up with 3.78 divided by 0.021. And that gave us 180 for our spring constant. Several of your answers, if you're using any of the practice problems in the book, a lot of your answers will be provided in scientific notation. So if you haven't had a chance, check out that video and make sure that your exponent is correct. Most of these problems are pretty straightforward as long as you're able to identify your given information, which is normally one of the areas that takes a little bit more time than others. The other concept we're going to talk about is our new vocabulary. We're going to acquire quite a bit in this particular unit. So, if I take a pendulum and I attach a pencil at the bottom and move paper under it as it's swaying back and forth, it will create a wave. What we're going to learn is parts of a wave are going to be different. So imagine we have the fluffier part or the rounder part of a wave, which is where motion is. This is your antinode. And we have the parts that are pinched in where there's no motion, and these are your nodes. In this particular example, we have a wave that has 3 antinodes and 4 nodes. Remember that there is no motion at the node. There is only motion at the antinode. We're also going to talk about harmonics. Harmonics are kind of based off of the number of antinodes that you have. If you look at our first example, there's one big bubble. This is your first harmonic. So our first harmonic has 1 antinode and 2 nodes. Right here, we have how many antinodes? 1 bubble, 2 bubbles, 2 antinodes, and how many nodes? 1, 2, 3 nodes. There's no motion at the node. There is motion at the antinode. This is your third harmonic. This will be your fourth harmonic. So count the number of antinodes that you have, and that will be directly related to your harmonic. If you have any questions about part 1 or part 2 of this video, be sure to send me a quick email and let me know exactly where you were stuck. Also, feel free to bring those questions to class. It makes for a great discussion on the next class day. I've also included a link with a classic video that can be seen in any high school or college, so it's definitely worth a look. It does a great job at introducing the topics. It'll also show you some of the vocabulary that's meant to come your way. I'll see you guys in class.